to fatigue. So when you think of yourself getting fatigued, it's not constant loading like we've seen. It's more about repeated loading. You go through cycles of stress, right, in day-to-day life, and this is what it's for materials too. When materials go through repeated cycles of stress, you have you have basically fatigue. So the things we've looked so far: static loading, this is uh, that is basically failure theories, was good for slow speeds. um, Light loads, and typically when you want to have large factor of safety, then you don't really care about fatigue. Okay, anything moving slow, anything which is light, anything with large factor of safety, you don't really care about fatigue. Now, if you're looking at dynamic loading, which is cyclic loading, okay, then you're looking at essentially fast speeds, high loads, and low factor of safety. You need to consider fatigue. So historically, uh, static loading was uh, a 19th century thing, because in the 19th century, uh, you really did not have steam engines and water wheel and turbines and so on. And so this is a result of the Industrial Revolution, which got in steam engine, water wheel, turbines. Yeah.
So static loadings were not concerned about fatigue, right?
Right.
But the dynamic loadings we should be concerned about fatigue, right?
Yes, absolutely. Put it here. Fatigue. And then this is just failure. So what happens with anything like a steam engine or a water wheel is a turbine is that is basically going to be subjected to loads in a cycle. It will be a max load, it will go to a min load, max load, min load. So there's a factor of um, repeated loading and unloading, and that process of loading unloading causes things to basically crack or break or deteriorate at a much lower load, and that's why we need to be concerned about static loading. So when there's fatigue, which is repeated high low stresses, would have failure occurs at much much lower strengths. Okay, so that will be lower than yield strength. Normally, when you have static loads, you get failure at yield strength, but this time, because of the fluctuations, um, you'll get failures occurring much earlier. Okay, so failure due to cyclic stresses is fatigue failure. Now, if let's see how to, well, if we want to be able to use materials for fatigue loading, we need to be able to predict when things will fail. So there are three methods for predicting failure due to fatigue. And I just list them down. Not that we're going to do all of them, but I should, I think, list them down. So fatigue life methods. Okay, there are three of them. Uh, so the but they, what is fatigue life methods? Here the goal is to predict the number of cycles to failure for a specific level of loading. Okay, in other words, think there is a think of there's a steam engine. We know that the loads on the steam engine will fluctuate from certain max, certain min. We know the loads, and we know that it's going to be subject to those loads for uh, n number of cycles. We need to predict the number of cycles n at which the material will fail for that loading. Okay, so the methods for doing that are the following. The first one is called strain life method. So this one uses, so when there's fatigue, what happens is there's invariably a crack forming in the material, and then that crack grows. So uses crack nucleation. Nucleation is another word for growth to predict failure. The strain life method. The second one is linear elastic fracture mechanics. Just like we run solid mechanics, there's a whole field called fracture mechanics, which tells you when cracks are formed, how they would propagate and how that would lead failure. So this one uses crack propagation to predict failure cycles. Should also be cycles, actually. Cycles. So the difference being that this one uses nucleation, the start of cracks. This one uses crack propagation. So the crack has already been formed, and now you want to use that to predict failure. Okay, and the third one, stress life method. This uses empirical test on test specimens. So think of lab tests to predict failure cycles. Okay, now, yeah.
So the first two are basically, like, you would evaluate that on like something that's already in service, which is the third one.
No, third one also is similar in service. Just that what you'll do is you'll do a test in the lab, you see how it breaks, and make some conclusions about what would happen if somebody was actually in the experimental settings, let's say the wheel of a train, locomotive, or so on. The third one is purely data driven. This is entirely data driven. While these two, there's like a theory behind it. There's a theory, just like we have a theory for predicting. We have a theory for predicting what do you call the normal stresses, shear stresses. This is a theory behind it, and 1, 2 is beyond. So 1, 2, if you want to learn, it's probably would be taught in an advanced solid mechanics class. Okay, where they actually will tell you how to come up with these theories for failure, and then use those. The one which we would use is number 3. This we will use this approach. Okay, this basically is how we've been doing things. We have, for example, a bar which is subjected to stress, and then we see where it cracks. We draw the stress strain curve. From the stress strain curve for ductile material, we found out the yield strength, ultimate strength, and so on. And that was used to make a failure theory. So this 3 is sort of line with what we have done so far. Okay. It's, I think, a very reasonable approach, which is you do experiment in the lab, you make a table, a database, and then use that to predict in the real world. Okay, so let's see how we will use number 3.